This is a GCSE lesson on ionizing radiation. So let's start with a quick question. What does this sign mean? And what could happen if you ignored it? Pause the video if you want to consider. This sign represents danger of ionizing radiation. And what could happen if you ignored it? Well, anything from feeling a little bit sick or getting burns on your skin through to dying. Ionizing radiation is extremely dangerous. It depends on the context in which you experience that ionizing radiation and the type of ionizing radiation, and that's what we're going to be introducing this lesson. So our title is Ionizing Radiation, and the first thing I want you to do is define the terms isotope and ion, draw a helium atom, then state the relative atomic mass and relative charge for each part of an atom, and then list the electromagnetic spectrum in order from lowest energy and frequency to highest energy and frequency. Pause the video to attempt these questions now. So let's start with isotopes. Those are different atoms of the same element. That is to say, these atoms all have the same number of protons, so they might be all, say, lithium atoms, but they have different numbers of neutrons. So these are atoms of the same element with different atomic masses. Meanwhile, an ion is simply something which has gained or lost electrons. So this could be an atom of lithium has lost an electron. So normally it would have 3, but one of them's gone missing. And so now we have a positive lithium ion. Alternatively, we could have chlorine, which has gained an electron. Normally, it would have 17 electrons. And let's say it's gained 1 to get 18 electrons. This leaves a negative chlorine ion. So that's an atom which has gained or lost electrons. Next, draw a helium atom. Well, if you've drawn it correctly, in the center you should have 2 protons and 2 neutrons. And outside, orbiting that atom should be, that nucleus are 2 electrons. State the relative atomic mass and relative charge for each part of the atom. Well, first of all, relative atomic mass of protons is 1. Relative atomic mass of neutrons is 1. And relative atomic mass of electrons is 1 over 2,000. So it's very small. You need 2,000 electrons to get the same mass as a proton. And the charge for protons is +1, for an electron is -1, and for a neutron it is 0. And finally, list the electromagnetic spectrum from lowest to highest energy and frequency. We have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and finally, the important one for today's lesson, gamma rays, the most high frequency and high energy electromagnetic radiation. So in the late 19th century, scientists made a groundbreaking new discovery. Some elements appeared to be giving off an invisible radiation, which would turn photographic paper black. Uranium was the first such element, but many more followed. Figure A shows uranium dioxide fluorescing under UV light. Now a quick note. The fact that uranium ore fluoresces, as shown in figure A, has nothing to do with its radioactivity, despite what the cartoons like The Simpsons tell you. Its fluorescence is due to something to do with the electrons, not to do with the nucleus of the atom. We'll look at fluorescence in a later video on the electromagnetic spectrum, in particular UV light. So, unstable isotopes. It turns out that if the number of neutrons in an isotope is too high or too low, or the nucleus is too big, the isotope can transmute into another element, into a new element, or a more stable isotope of the same element by releasing a particle from the nucleus. This process has been named radioactive decay, and the particles released from the nucleus is the invisible radiation discovered by Becquerel. Uranium-238, as shown in figure B, is one such example of an unstable isotope. So, I'd like you to write down the sentence starters along with the answers to those questions. Now, there are three types of ionizing radiation. They can all be emitted by an unstable nucleus. They have been named with the Greek letters of the alphabet: alpha, beta, and gamma. In fact, this is where we get the term alphabet from. The Greek alphabet starts with alpha and beta, so we have alphabet. So what are they made of? An alpha particle is made of 2 protons and 2 neutrons. Essentially, it is the same as a helium nucleus. So this means that a heavy element like uranium-238 literally loses 4 of its nucleons in one go and becomes a new element, thorium-234. So rather than just emitting a proton on its own or a neutron on its own, one of the most common types of ionizing radiation is to release all 4 in this big chunk. Next, we have beta minus particles. These are fast-moving electrons from the nucleus of an atom. These are emitted when a neutron inside a nucleus becomes a proton. In order to do this, an electron must be created. So because of a law of the universe called conservation of charge, you can't just create a positive charge out of nowhere. If something becomes positively charged, something else must become negatively charged. And so a beta particle spontaneously comes into existence when a neutron becomes a proton. And finally, gamma rays. Gamma rays have no charge or mass, but are high-energy electromagnetic waves. They're that last part of the electromagnetic spectrum we mentioned. They are released after a nucleus decays by alpha or beta, because the nucleus gains vibrational energy, which it must lose to become more stable. So you can imagine it like the nucleus wobbling, and the nucleus needs to release that energy. Copy down the sentence starters and complete the questions you can see on screen. So let's look at how they actually ionize things. So, figure D shows an alpha particle colliding with a neutral atom and its result. The electrons from the neutral atom are taken by the alpha particle, leaving an ion. This happens frequently because alpha particles are the most massive and have the strongest charge. So you can see an alpha particle colliding with a neutral atom. The alpha particle has now stolen 2 of the electrons, leaving that atom as now an ion. It's no longer an atom, but an ion, because it has lost 2 electrons. Next, figure E shows beta minus particles colliding with a neutral atom and the result. So this time, the beta minus particle has energy as it's traveling. It's got kinetic energy, and it might happen to knock into another electron, knocking that electron out of the atom. Once it's done this, it leaves behind a positive ion with a charge of +1. Meanwhile, that beta particle may go on to collide with another atom, as will the particle, the electron that it's released. So both electrons may go on to ionize something else. However, each time they're losing kinetic energy, so this effect becomes weaker and weaker. And finally, figure F shows a gamma ray colliding with a neutral atom. The gamma ray is absorbed by an electron in the outer shell of a neutral atom, giving it enough kinetic energy to escape the shell, leaving an ion. So this time, the electron is absorbing that energy from the gamma ray, and that makes the electron move much faster, so fast that it can escape the orbital. It can jump from that energy level away from the atom completely. It's been given enough energy to escape that atom. This happens rarely because gamma rays are massless and have no charge to attract them towards atoms. So this means they do not interact with atoms very often. In fact, to get them to interact with atoms, if you want a lot of interactions, you need a very dense substance with a lot of electrons in it, like lead. Copy down the sentence starters and complete the sentences. Now, this is the textbook page if you'd like to read it. And you can see the questions there are written at the bottom right. Finally, problem solving. Compare and contrast. So, compare and contrast the mass of an alpha, a beta, and a gamma, and then compare and contrast the charge of an alpha, a beta, a gamma. And state the charge of a strontium ion if its atom were bombarded by a single alpha particle, what it would be if it was bombarded by a single beta minus particle, and what it would be if it was bombarded by a gamma ray. Finally, compare the relative ionizing potential of alpha, beta, and gamma. Which one is the most ionizing and which one is the least ionizing?